Welcome to Learn OpenMV in 1 hour. This quick and practical course will teach you how to create real-time computer vision projects using the OpenMV camera, no advanced coding required. You will learn everything from installation and general-purpose scripting to edge detection, QR code scanning, person detection, color detection, and a lot more. The course is led by Mr. Mashood, an experienced instructor in embedded vision and robotics. Whether you are a student, hobbyist, or an educator, this course is your shortcut to getting started with vision projects. Let's dive in.
Hey everyone, let's begin this series by understanding what OpenMV actually is. OpenMV is a compact, Python programmable computer vision camera designed to bring computer vision capabilities to embedded systems. It runs MicroPython and allows you to easily write image processing, object tracking, and machine learning programs all using Python code. It is built specifically for students and developers who want to add visual intelligence to their projects without needing deep knowledge of image processing or AI frameworks. In short, OpenMV lets you build smart, vision based projects with ease and minimal hardware setup. All you need is the OpenMV camera and a Type A to Micro B USB cable to connect it to your PC. And thirdly, the OpenMV IDE to write, run, and build OpenMV projects. You can insert SD card here to overcome the memory and performance limitations. Throughout this series, we will be working specifically with OpenMV Cam H7 Plus. I am showing the web page of OpenMV Cam H7 Plus. This model is capable enough to run computer vision and machine learning tasks in real time. It is ideal for learning, prototyping, and building small to medium scale embedded projects. We won't go into technical details, that's not the goal of this beginner friendly course. We will learn how to set up OpenMV Cam and install its IDE, a walkthrough of IDE features, running and understanding built in examples, creating simple but effective custom projects, and using the camera for real time applications like face tracking, QR scanning, and more. So let us now discuss the documentation for OpenMV. You can access the documentation by following this URL. Here we will just have the bird's eye view of the documentation. For getting started with OpenMV, almost everything will be discussed in the course. And if you want to master the OpenMV, you can read the documentation in depth. We have the section of software setup. The core idea of this section is that before you can use the OpenMV Cam, you need to install the OpenMV IDE, and the installation steps vary slightly depending on the operating system, whether you are on Windows, on Mac OS, Linux desktop, or you can say the Raspberry Pi. Then next we have the section of hardware section. The notion of this section is that before connecting the OpenMV Cam to your computer, it is recommended to clean the camera sensor with isopropyl alcohol and a lint-free cloth to ensure a clear image. After cleaning, you can reattach the lens and wait for the device to be recognized. You should also see a blue LED and a mounted USB drive on your system. Then you can connect through the OpenMV IDE. And when the camera is connected, it shows up like a USB flash. And since the OpenMV camera uses the FAT file system, it is prone to corruption. And if you write files during power loss or heavy script execution, so you are advised not to write this internal drive from Python scripts. Instead, it is just manually store assets like models or data files. And what we other things we have in the documentation are the information about the IDE. We have the upcoming discussion about the IDE in detail. So if you want, you can read it along. The one thing more I will discuss from the documentation is the connecting to your OpenMV Cam. So it says that OpenMV IDE needs to be associate the USB flash drive on your OpenMV Cam with your OpenMV Cam's virtual serial port so it can parse compile error messages and open file with the error easily. Instead of reading from the documentation, we practically implement and connect it to our PC. So let's do it. So I have opened this PC in my computer where devices and drives appear. First I will connect the OpenMV Cam without the SD card. As I have told you that you need a micro B type USB cable. When you plug in the cable to your PC and OpenMV Cam is attached to the other side of the cable, a new device with the name of OpenMV appears. You can see the storage of 23.9 MB it is giving. And when you plug in the cable, first a green light from the LED turns on and then a blue light starts to blink unless the OpenMV Cam is connected using the OpenMV IDE. The process we currently did is plugging in the OpenMV Cam, not connecting to the PC. Actually, the connection requires the IDE. Now, I will plug in the camera with an SD card inserted inside. Now the drive will appear just like a USB drive with the storage of your SD card. The most important thing to notice is that if the blue light does not start to blink, there may be any fault with the hardware. And once you plugged in the camera, a file named .openmv underscore disk should always appear inside the drive of OpenMV. No matter the OpenMV is with or without the SD card, this file should always appear. And if this file does not appear, there is a problem, or you plugged in the OpenMV Cam to your PC for the first time. And for the first time, to see this file, you need to boot the OpenMV Cam. And the boot process is very simple and straightforward by clicking the OK button. When you see the notification appeared on the screen for the first time, you plug in your OpenMV Cam. So that's it for the introduction of OpenMV. Hey everyone, welcome back. Let's now get hands-on with the OpenMV IDE, the software we will be using throughout this course. This is where all the coding, testing, and camera interaction happens. We will install the IDE and set it up for the first time. Also, we will walk through the interface. Whether you are on Windows, Mac OS, or Linux, the installation process is simple and well supported. You can access the downloads by going to your browser and write OpenMV downloads and hit enter. This will land you on a page from where you can download your IDE. So you will download the IDE as supported by your operating system. I will install for Windows. So once the exe file for Windows have been downloaded, we will double click to install it. Next, you can browse your folder where you want to install this IDE. I will hit next, accept the license, then again hit next, and you can enter a name to create a new directory for your IDE. I will keep this as default and then hit next and then install. I will not install this because I have already installed. So the installation process is very straightforward. You can hit install and can start work with OpenMV IDE. So once you open the IDE, this helloworld.py file opens by default. So we will close it now and we'll discuss it later. The first thing you have to make sure after opening the IDE is the connection to the OpenMV camera. So once I will connect, it will say that no OpenMV cam found because I have not yet plugged the camera. Once I plugged in, the icon will be changed a little bit. So let's plug in the camera. As I have plugged in the camera, you can notice the change in the appearance of icon. So by using this, you can diagnose that if your OpenMV camera is safely plugged in or not. So once you notice the change in the appearance of the icon, you can click to connect the camera. So the icon again changed. This determines that your OpenMV camera is plugged in and also connected. You can click this icon again to disconnect. Then you have the menu tab on the top. From the file menu, I can create a new file, open any existing file, and then I have the examples tab. This examples tab is very important. We will discuss all of the important examples later in the tutorial. For the time being now, I will open the helloworld.py. So this is the code editor. In this window, you can edit your code, and then this button will be used to run the script. And the video feed or camera feed captured by OpenMV Cam will appear here. So let us discuss the examples tab. OpenMV is providing you built-in examples. You can just click to open any file and then execute. As you can see, there are so many options. As you can open this file helloworld.py, this is the basic file that will take a picture and print or show the results in the camera feed. And then we have the camera tab. Using the camera, you can take snapshots, record any video, optical flow that provides absolute rotation, differential rotations that tracks how much the camera rotates left, right, forward, back, or sideways. And these differential rotations work for smaller, more detailed movements. Then we have the image processing section. And then image processing contains drawing like arrow drawing, circle drawing, or image drawing, text drawing that shows how to overlay visual elements on the camera feed. You can portray arrows, circles, images, or text to visually appear on the camera feed. Then again, we see others like we have the most important machine learning tab here. Machine learning provides us TensorFlow and HAR Cascade. These are two important tabs. Discuss them later in detail. TensorFlow provides you image classification to classify between yes or no. Then you have the object detection and also the regression to predict a continuous value instead of a category like yes, no, and all like that. Then we have the barcode section in which the built-in files provided to detect a barcode, to detect a QR code. So let us open this QR code file. What this file does, this will detect a QR code that will be brought forward in the front of camera. Once I execute this program, the camera will start capturing the frames. So in front of camera, if I bring any QR code, it will print the QR code information in the terminal and the video feed in this frame buffer. Then we have the feature detection portion in which you can perform the edge detection, find circles in the camera feed, or you can template matching like match two things or shapes. For example, you have to perform face recognition, you can match two faces. If they match or not, this will work for the face recognition in a very simpler manner. Then we have the apparel tags. These are just the advanced QR codes widely used in robot navigation or object tracking. So you can use any built-in file according to your use. As just like the QR code, this will detect the apparel tags brought in front of the camera. Now we are pretty much done with the examples. We will discuss each, or you can say as many as we can useful examples later on. Then we have our tools tab. From the tools tab, we can load custom firmware. This lets you manually upload a firmware file to the camera. Currently, the OpenMV work with the default firmware, and if you have prepared any your custom firmware, you can load it that file from here. Then you can erase internal FAT file system. This clears the camera internal storage and it is very helpful when the camera storage is full or behaving unexpectedly. Then you have the ROM file system. These options allow you to create, manage, or you can say edit the read only space on the camera. Then you can check this option to auto reconnect to OpenMV camera. So once we open the IDE, we don't need to click this icon to connect our camera. If you open the IDE and your camera is plugged in, this will connect automatically by using this option. So I will click it. Then we have stop script on connect disconnect. This will stop the execution of the script if the camera is disconnected, or like we try to connect it again. This action will stop executing the script, and then this will open the drive folder where the files saved on the OpenMV camera appears. So everything you save, any images, any files, any recordings, these will appear in this new volume. So then we have the option of resetting the OpenMV camera. This option restarts the camera hardware, just like unplugging and plugging it back. It is useful if the camera becomes unresponsive or for viewing the recently saved file on the SD card. By the way, I just realized that I accidentally missed showing an important tab under the tools menu, and it suddenly came to my mind while wrapping up. So let me show you that now. Under the tools, there is a tab named Machine Vision. This includes utilities that help you work with trained machine learning models directly in the IDE. You will find Open Model Zoo, a built-in collection of ready-to-use TensorFlow Lite models. Then Convert Model for NPU, that is used for converting models to run on the hardware with neural processing units. Then you have the Threshold Editor for fine-tuning color detection, the Key Points Editor used for training template matching or key point models, and various generators like Apple Tag Generator, QR Code Generator, Barcode Generator. So let us open this Model Zoo. In the Model Zoo, you will see several folders grouped by source, for example, the Edge Impulse and Google. Let me open these folders. First we have Edge Impulse, and then provided by the Google. There is a file name FOMOFaceDetection.tflite, a fast object detection model provided by Edge Impulse. Then we have MNIST LSTM.tflite, that is used for recognizing handwritten digits. If you worked with TensorFlow, or like have you ever started deep learning, you will be familiar with this MNIST dataset. And then we have person underscore detect.tflite. That model will be used to classify whether a person is present or not present in the given camera feed. We will discuss it later in the upcoming projects. So these models are ready to be loaded, tested, or even directly used in your projects without any training or setup required. Then we have the dataset editor. It is very useful, and we can create a new dataset and open the existing dataset or export any dataset from Edge Impulse. So if we click this new dataset creation, then we have to create a new folder. For example, I create a folder here by the name, you can say, data set, and then I click this folder. So automatically OpenMV created this file for me. By using this file, I can capture images or create my own dataset. There is the space available here. I can comment out these lines or remove these lines and put my logic here to capture pictures according to my need, and then feed it to this dataset, and it will be eventually saved to the folder that I have recently created named the dataset. So from here you can create new classes inside the dataset. If you are familiar working with the dataset, you know what classes contribute. So this was the general introduction of how to use OpenMV IDE. That's it. Hey everyone, welcome back. Before we dive into any specific OpenMV project, let us first understand the basic structure of almost every OpenMV script. Whether you are detecting objects, tracking colors, or running lightweight AI models, Most projects start with the same code pattern. So in this video, we will look at what is called the general purpose code, or you can say the hello world code. I will create a new file from here. In the very beginning, I will perform the imports. Import sensor. What this module does, this controls the OpenMV camera. You will use it to set resolution, color format and capture images. Then we have time module. What it does, it is used to measure how long each frame takes. Actually, it calculates the frames per second and it will be usable throughout the program. Then I will perform the camera initializations. At first we have sensor dot reset, right? It wakes up the camera and reset all the previous settings. Then we have sensor dot set underscore pix format. What it is responsible for, it tells the camera to capture color images, and we are passing here sensor dot rgb65. If you wanted grayscale, you would use grayscale instead of RGB. We want RGB, that's why I write here sensor.rgb565. Then we have sensor.set underscore frame size. Then we will pass QVGA inside it. What is QVGA? Actually, VGA stands for Video Graphics Array, and it has the standard resolution of 640 by 480. And here we are using QVGA. Q stands for quarter, half for the height and half for the width, and it will be eventually equals to 320 by 240 pixels, right? Actually, we have to write the sensor along with it also, as we did above here. So I will write sensor here also. Sensor dot, sorry for the spellings again, sensor dot QVGA. Fine. All right. Then we have our last camera initialization, sensor dot skip frame, right? It tells the camera to wait for a while. We pass time equals 2000. This 2000 corresponds 2 seconds. So this line of code tells the camera to wait for 2 seconds, just enough time to adjust exposure and white balance before starting. Then we initialize a new variable, clock equals time. We will use the time module as we have described above, dot clock. This line creates a clock object. We will use it to track how long each frame takes and eventually calculate the frame rate. Then we will move towards the main loop of our program. First we have clock dot, this starts a timer for the current frame. Then we have img equals sensor dot snapshot. Fine. It takes a picture and stores in the variable img, right? You can later process this image to detect faces, track colors and anything you want. Then we will simply print the frames per second. Clock dot fps. Fine. This line will print frames per second in the console. You can open the console or terminal from here. Once I will execute the program, the frames per second will be printed here and the camera feed will be visible here. So this is the general purpose code. We will use this as a template in every upcoming OpenMV project. We use these imports, we use these camera initializations, then a loop, main while loop, in which we will perform the image capturing and other functions related to it. We will discuss it later in upcoming projects. So let us execute this program to see the results. First of all, save the file to run the program. Then we will execute the file from here. As you saw that the camera feed appeared here, I am not visible, maybe I am a ghost, and also the frames FPS are printed here. Once I will execute this again, this will start printing the frames per second again, and also the camera feed, whatever is in the front of camera. So this is the general purpose code, and or you can say the hello world file, like every programming language use this file for the purpose of starting programming. You can also find this example from going to there. You will go to examples, and then you have hello world and hello world.py. This is the same file I write it from scratch. So that's it for this video. Thank you. Hey everyone, welcome back. As we are pretty much familiar about the OpenMV features and how the code works in its IDE, let's now explore some of its useful built-in examples provided by default. For opening the example, I will go to the File menu, then click the Examples, and from Examples, I will pick the Feature Detection, and we have the file of edges.py. Actually, these examples are designed to help you quickly understand the camera capabilities. And today we are looking at edge detection. This technique helps the camera to detect the edges in the camera feed, and it finds the outlines of the object. It is very useful in a wide range of projects like shape detection, object tracking, or motion analysis. Let's walk through the code together. As we are familiar with these two modules, the import of sensor module and the import of time module, which controls the camera sensor and tracking the frames, or you can say the FPS, frames per second. And also we have a third module here, we will discuss it later. And then I will move toward these camera initializations. Nothing new here, we already know that. We have covered things like resolution, color format, and frame delaying. The one thing new here is gain ceiling. This sets the maximum gain level that the camera can apply to brighten the image. In low light, this helps make edges more visible, but it can also increase noise. So setting a gain ceiling of 8 give a good balance between visibility and clarity, which is especially helpful in grayscale modes we are using here. Then as usual we are tracking FPS here, and also the capturing snapshots and assigning them into the variable named img. And we have the main loop of our program. Now here something new comes in. As we have imported the image module above, it will be useful to detect the edges. The image module provides the access to powerful processing functions like find edges, and it gives us the constant like edge canny. So this whole line applies the canny edge detection algorithm to the image. And also we are setting the threshold here. The first value is the low threshold. It says that any edge weaker than 50 is ignored. And the second value is the higher threshold. And it is saying that anything stronger than 80 is definitely considered an edge. So this will help us to avoid noise and keep only the important outlines, or you can say the edges. And after tracking the frames per second, we are printing them into the terminal. Let's run the code and check the usability of this built-in example. So after the delay of 2 seconds, the edge detection has been started. It is detecting all the edges between these thresholds. So we can see different objects and their edges have been detected. So that is the built-in example for canny edge detection using OpenMV. This script is great for extracting object outlines from the camera feed and can be the first step in most advanced vision tasks like contour analysis, motion detection, or even shape recognition. So that's it for this built-in example. Now let us move on a really cool built-in example, QR code detection using OpenMV. I will open the example from here. Perfect. With just a few lines of code, the OpenMV camera can detect a QR code in the camera feed, draw a rectangle around it, and even prints its data all in real time. This can be used for automation, product scanning, inventory systems, or even triggering events for encoded message. Let's walk through the code and break it down. Everything above here is as usual, the import of sensor and time module, the camera initializations, but this is the new line we have here. This line disables the camera auto gain control. But why it is needed? Because auto gain can adjust the brightness in a way that distorts the QR code's black and white patterns. And this will make the detection less accurate and even impossible. So to get clean and reliable QR detection, we turn off the auto gain. Here we are capturing the image using sensor.snapshot, and then immediately we are using the find QR codes function. So what does find QR codes actually return? It returns a list of QR code objects that were found in the frame. Each object contains useful info like position, size, and actual encoded data. Then we go through the list using the for loop. So if there are multiple QR codes in the frame, this will run for one each frame. This line draws a red rectangle around the detected QR code. Code.rect give us the position and size of the QR code. Basically the XY position, width and height. And the color of the rectangle being drawn is red because we are passing 255 value for R and 0 for the green and 0 for the blue. And at the end, we are printing the detected QR code. It will print all the information related to that QR code in the terminal. So let us execute the program to see the results. As we have seen the red rectangle being drawn around that detected QR code, and also the information of that QR code is being printed in the terminal. The XY coordinates of the QR code, the width, the height, the payload. Payload is actually the data inside this QR code, and also the version and all other things related to that QR code. So here we are done with the sophisticated but the simplest project. So here we are done with the simplest but a sophisticated project which is provided by default. There is one more thing here, that is img.lens correction, and we pass the value 1.8 inside it. This function corrects the lens distortion that comes from using a wide angle lens. Without this, the QR code near the edges of the frame can appear curved or stretched, which can make detection harder. So overall, we can say that this line helps the QR code shape more rectangular and readable, especially near the edges of the frame. So here we are done with this project. This is the simplest but sophisticated built-in example provided by OpenMV. Hey everyone, welcome back. Let's now try a new powerful built-in example, one that uses a trained machine learning model to detect whether a person is present in the frame or not. I will open the example by going to File menu, then Examples. From Examples, I will pick the machine learning, go to the TensorFlow, and finally pick this file. This is TensorFlow Lite Person Detection example. This example introduces us to running a TF Lite model directly on OpenMV Cam. Let's get started with the model itself. This line loads a machine learning model named persondetect.tflite. This file is stored inside the OpenMV firmware under the ROM folder, which means it comes preloaded and ready to use. So there is no need to train or upload anything extra. It is already available on the camera. Now what is this TF-Lite file? This stands for TensorFlow Lite, a lightweight version of TensorFlow models that is optimized to run on low power devices like microcontrollers and cameras. So this TF-Lite file contains a pre-trained model that knows how to classify an image as either a person or not person. Now let us comment out the whole code and just print the model. As I have executed the file, you can see the model details in the terminal. This line prints the model. So these are the model information. This model size shows that the model is around 300 KB in size. If we convert these bytes into KBs, then we have the input shape given to the model. In this case, the image size is 99 by 99. The batch size given to the model is 1, and also the channel of input is 1, which is grayscale. Then we have our output shape. This tells that the model gives us two output values. The output values are two, which are classes of person and not person. And again, the same batch size is 1. And these input scale and output scale are used to convert image data into format that model understands. And rest of the details are related to the memory and helps OpenMV to handle the model efficiency. Now we will bring back these line of code. So this code snippet is the matter of discussion. The comment above is saying that this combines the labels and confidence values into a list of tuples and then sorts that list by the confidence values. What does this line means? This says that the labels and the confidence values turned into list are sorted by the confidence values. The labels will be two. One label is person and the other label is not person. As we are classifying this thing that object in the front of camera is a person or not a person. So there are two labels. And then we have the confidence of being a person or not being a person, and this is flattened into a Python list. This model.predict runs the image through the model and return the results. You can say an array of confidence scores. And we have this zip function that pairs each label with its confidence. This is the label and this is the confidence level, which are zipped together. And this key tells that sort the list by the second item of each tuple. So this first index tells that we are sorting the list by the second tuple, by the second item of each tuple, and which is obviously the confidence score. Then we have reverse set to the true, which means put the highest score first. What is score? The score of confidence level for being a person or not being a person. So after sorting, the label with the highest confidence comes first in the list to print the predictions by the model. This calculates FPS. Then we have the label with the highest confidence and also its confidence score. So this will print the label of person or not person, and this will print the confidence of a person or not being a person. So let us run this code to see the results, what this model is predicting. As you can see, when the person is visible in the camera, it is printing the label along with its confidence. And when the person is not visible in the camera, it is printing the label of no person with its confidence level along with the frames per second. So that simple is the person detection. So here is how we load a pre-trained TF Lite model for person detection, run predictions on live camera feed, pair labels with confidence values, sort them to find the top prediction, and then finally print out the result with the frame rate. Hey everyone, welcome back. In this video, we are going to create a custom OpenMV project. We have already explored enough built-in examples, so now it's time to try something on our own. You can continue to explore other examples yourself, but this one will help you understand to build real and usable projects from scratch. I will create a new file to start writing the code. So what this file does, it will perform color detection. Anything colored object brought forward in the front of camera will be detected, and the color detection will be based on threshold we set. We will discuss about the threshold later. If we set the threshold like red, blue or green, it will detect the respective color. So let's start writing the code. First of all, I will perform the imports of desired modules. So if you followed along the tutorial, you know the importance of these modules and how they will be utilized. Then I will perform camera sensor initialization. So nothing new here. We have already discussed these camera initializations before. Then we set the threshold to detect the specified color. In this program, we will set the threshold to detect the red color, and I will set the values in front of you. So here I defined the red threshold. So here I created a variable and passed a tuple to it. There are total 6 values inside this tuple. These first two numbers control lightness, how light or dark the object is. The next two numbers control the A channel, which goes from green to red. Higher numbers mean more red. Then these last two numbers control the B channel, which ranges from blue to yellow. In red objects, we usually want some yellowish color. So these values help fine tune the red detection. So if you want to adjust how bright the red color should be, change the first two numbers. And if you want to narrow or widen the red hue, change the A channel values. And if you control the yellowish red tones, you can work with the last two numbers. Then we will start writing main loop of our program. Again, nothing new here. You already know the purpose of these lines of code. The main thing that has the major impact on this file is the find blobs method provided by OpenMV. We will utilize this method in this way that what this line of code does, it looks for an image and tries to find areas or blobs that match the red threshold. It only considers the blobs that have at least 200 pixels value. And also we can check that the area of blob is big enough or not by creating a new parameter here. So we are all done. This function returns a list of blobs, one for each red object found in the image. Now that we have the blobs, now we can loop through them in this way. So for each blob, a red rectangle has been drawn around it. A white cross will be placed at its center. That helps visually track the position. And finally, we will print the X and Y position of the detected colored object. Now I will execute the program to see the results, if the red color is detected or not. As far as I executed the code, I got an error, and the issue is that this code snippet will come under a for loop, because this will return a list of blobs. Then using the for loop, we will traverse each blob one by one. The code is fixed now. Let us execute the program. As we have seen successful execution of the program, the red rectangle is drawn around the red color, and also the white cross has been used to placed at the center of the detected colored object. And now you can also define new threshold to detect other colors like blue, green. So you have to declare new thresholds here. Also you can define the green threshold to detect the green colored objects. Now you can use this threshold. You just have to copy the name of variable and paste it there. It will automatically detect the blue color for sure, and same for the green. Right now I am commenting out this code. You can use it on your own. So that's it for this video. Thanks for watching. Hey everyone, welcome back. In this video, we are going to create a new custom project that performs face tracking. First it detects the face and then tracks it until the face goes out of the camera range. First I will create a new file and then start writing the code. Whenever we create a new file in OpenMV IDE, this boilerplate code appears automatically. As we are familiar with these modules, the sensor module for controlling the camera sensor, the time module responsible for handling frames per second and related tasks. And we are also familiar with these camera initializations, and nothing new here. For the sake of this project, let us first detect the face in the camera feed. For this, I will define a new variable, face is equals to img. I will utilize the img, the snapshot we are having above, img dot find underscore features. This function will return a list of faces in the camera feed and store that into this variable. The first parameter of this function is we need a face underscore cascade. From where this face cascade is coming, we have to define it outside the loop. For defining the face cascade, I will write the variable name face underscore cascade equals, and I will utilize a new module here named image. So I will import it here, import image, and then utilize the powers of image. From image, we are using the har cascade. And also I am writing the path of the har cascade which is residing in the ROM of the OpenMV. I will write the path for it slash ROM slash har cascade underscore frontal face dot cascade. Alright. And also we have a parameter of stages equals 10. Here we are using a pre-trained har cascade model that is already stored in the OpenMV ROM. The stages equals 10 part means the detection will run through the first 10 stages of the model. Using more stages gives more accurate results but takes more time. After that, I will pass new parameters here, naming threshold equals 0.5. Actually, it controls the confidence level. The confidence level tells whether it is a face or not face. Lower value will allow more matches but also some false detections. So we are keeping it average of 0.5 confidence level. Then we have scale underscore factor equals 1.25. This helps the detector to scan for the faces at different sizes. Higher values run faster but may miss the smaller faces in the camera feed. So as we have detected the faces, now it's time to draw the rectangles around the detected faces. For this faces, if we found any faces, then for R in faces, as I have told you above that find feature return a list of faces, then we will draw the rectangle around each face. I will again utilize img dot draw underscore rectangle, and I am passing the R. R will traverse each face in this list and draw a rectangle around it. So we are pretty much done with the code. Let us save and then execute the file. As we have seen the execution of code, the detection is not so much efficient. It is also detecting some faces here. You can say some false detections. So we have to define a region of interest to only focus this part of the camera feed. So it will truly detect the faces rather than any other object in the camera feed. So let's do it. Now I will pass this R inside a new variable named tracked face equals R, and also adding a break statement here to exit the loop, and also this time we need an else condition. Else, for the time being I will not write the code here, we'll add some code later on. Now if a face was tracked previously, if tracked face, define a region of interest around it. Y, W, H equals track underscore face. So here we are having an undefined variable. We have to define it above underscore, and I am passing none here. What is the purpose of doing this? Actually, we are passing this R to this tracked face, and this tracked face is going above. We are extracting values of x, y, width and height from this track face. As I have told you that we get the list of faces, and these faces are in the form of tuples. Every time you do this thing, it will return a tuple like x, y, width and height. It returns the x and y position and width and height of the detected face. So we are extracting each value to define our region of interest. ROI, I will be using the abbreviation ROI for region of interest, equals, first we have max of x position minus 20 and 0. It will pick the maximum value between 0 and 20 minus by the x position of the face. Then we have max of y position and same as above, minus by 20 and 0. What we are doing here, we are subtracting 20 from x and y position to look little above to the left. As this is the position of face, we are subtracting minus 20 so that it look little above to the left to find the accurate faces. Then we have minimum of width of the face plus 40, and the other is img dot width. We are making sure that while expanding the region on width wise, it does not go outside the bound of these img widths. What is img? Img is the captured image frame. Then we have minimum of height plus minimum of, sorry for the mistake, height plus 40, and as above img dot height, and then close the parentheses. So now the model will detect the faces according to this region of interest, and we are passing this region of interest in the find features ROI. ROI is equal to ROI, this one, right? Actually, this tells the camera only search for a face inside a smaller region. And if we don't have tracked any face yet, then there should be also another check. Outside the if condition, I will define the else. We will perform the full frame detection instead of using the region of interest if there is no face is tracked. So I will copy this code, Control C, and pasting it here without using the region of interest, as region of interest is related to the tracked face. So if we have no tracked face, then we will not use the region of interest and we will perform the full frame detection instead of using any small portion of it. Actually, I have to write this inside the if block so that it checks the condition correctly. So why this is an indent error, I will cutting it and again pasting it. Hope so it will work fine now. So the indentation error has also been fixed, and I will look in the code if there is something pending. So here we have our else condition pending. I will write the respective code here again, like track underscore face equals none for the safety check. So I will now save this code and execute the file to see that if we have improved results now or not. Again, we got into an error. Let us fix this by saying this error. Name faces is not defined. Let us run the code to see the error again. I think so. This is very unexpected error. I have looked into the code very carefully and I didn't see any issue. Let us execute this again to find it out. So let's once again run the code with the hope of that it will work now. I have completely checked the code and yes, you can see this is my detected face and it is tracking where I am going. There are no more false detection. It is accurately detecting my face, just the magic of defining the region of interest, and also it is tracking where my face is going. So that is the successful execution of the code. Right. Now face detection work faster and more accurately. It no longer detects any false faces from unrelated part of the image. It stay focused around the last known face, and thanks to that region of interest. That completes our face tracking and setup using Har Cascade and region of interest filtering. Hey everyone, in this part of project, we are going to take face tracking one step further and estimate how far the detected face is from the camera. This builds directly on our previous face tracking code and adds the ability to measure the distance using simple math and width of the face in the image. To calculate the distance, we use a method called pinhole camera model. Pinhole camera model. And this model carries a formula as given below. D equals uppercase W multiplied by focal length and all divided by width. So what are these values? This uppercase D stands for the distance of the detected face from the camera. W stands for the width of average adult human face. We take this value as the benchmark and put this in this formula to calculate the width of detected face. So this lowercase w is the width of the detected face. We have two different widths. One is the average adult human face width and other one is the detected human face width. So detected can be varied. This will work as the benchmark and it will be the fixed, and this can be vary according to the face sizes in the camera feed. So we need these variables to be defined. We have W equals 14.0. So the average width of adult face is 14 centimeter. So we take this value and it will work up and it will work as a benchmark to calculate the width of detected face. Then we have the focal length of the camera. In our case, the camera is OpenMV camera and the estimated value of the focal length of this camera is 160 pixels. So it is the estimated value according to the my environment. This value can vary according to your environment like brightness or the camera distance. So for the sake of this project, I took the estimated focal length which is 160.0 pixels. Then we need the width of the detected face. So currently we don't have the width, we will calculate. And eventually the distance, the main thing we need, and it is also set to the 0. So we are completely done with defining the variables that will be used in this pinhole formula to calculate the distance of the detected face from the camera. Now the things we know is the width of the average human adult face and also the focal length, and distance we have to find it, but currently we don't have the value of the width. From where we will get the width of the detected face, or you can say the tracked face, as we have done the project on it, so we will utilize that code to get the width. As we are tracking the face and we are passing this tracked face into these values. These values are x position, y position, width and height of the detected or tracked face. So the thing we need here is the this w value. We will extract this w value and pass it here, and it will calculate the distance for us. So we will extract the width from here. We can do this like w equals the above tracked face, and we need the second index. As there are, I have did a blunder. Okay, again w equals to tracked underscore face, and we need the second index. Why we need the second index? Because on the 0th index we have the x position, on the first index we have the y position, and on the second index we have the width of the detected face. So we extracted this second index and passed into this variable which is described or defined above. Now we are pretty done with our work. We have completed the formula. We got these three above values. Now we will calculate this distance and show this distance using a string. We can use a string to be drawn on the image. I can show you practically like that. I will use the mg dot draw underscore. The position for that string will be, the x coordinate will be 20, the y coordinate will be 30, and then we have the formatted string to print the distance. we have distance, and in curly braces I will pass the variable d, as we are getting this d from these values, and also we are printing this value using a drawString method. You can practically see how it works. So for that string, I will set its size, or you can say I scale this string to the value of 2, and also I will set the color of this string equal, I will pass the green color, r equals 0, g set to be 255, which will be equals to green, and also value set to 0 for the blue. So now we are done with the string, and for if the face is not detected, we also have to write the string for it also. So we will copy this part from here, and also we will paste it like that. If the face is not detected, we will say that no face detected, and we will remove this formatted string type, and also we will print the last distance we have captured. If no face is detected, the last distance will be printed as same as the above. Now we are done with our code. I will execute the code to show the practical example how we calculate the distance, then pass that distance in a string to be printed on the camera feed. And also when the face is not being detected, we will say that no face detected, and we will print the latest distance that has been calculated. So I will alter the position a little bit. I will pass the, these are the x or y positions of the string. This is the coordinates of the camera feed. I am setting that 2030 value of the, this corresponds to the x value, and this corresponds to the y value for the position of string that will be drawn. So let us now execute the code to see the results. As you can see, as I move back and forth, it calculates the distance and print on the screen. And if no face is detected, oh, there is an issue. The strings are printing over each another. I am fixing it. I will pass the x position for distance 50, and also change its color. It is no face detected, so it should be in red color. I will pass the red color here, 255 for the red, and G will be the 0 and B will be the 0. This is the RGB value, as everyone knows about it. Nothing to discuss this again. So let us execute the code again. So as you can see, the distance of the face has been detected. As I move back, the distance increases, and as I come forward, the distance start to decrease. So if no face is detected, it says that no face detected and prints the latest distance it calculated. And when again it is tracking, also measuring the distance of the face from the camera. No face detected, the last distance printed successfully. So that's how we made our recent project more efficient. Now a face is detected and tracked as before, and the distance is shown in real time on the image. So that's it for this project. Thank you. So finally, we have now explored the basics of using the OpenMV Cam through simple but effective projects. This was a beginner friendly introduction, and OpenMV offers even more advanced capabilities, especially in its latest versions. I hope to share more videos on these features in the future. As we have started by understanding what OpenMV is, how to connect it, and how it fits into real world computer vision projects. We walked through the IDE works, wrote general purpose code, and explored several built in examples from QR detection to basic machine learning. Then we moved on to custom projects, including the face tracking and distance measurement project. If at any point you noticed a mistake, faced an issue, or have a suggestion to improve, feel free to drop a comment under the video. I would be happy to help or improve future content. The OpenMV Cam is a powerful tool for bringing computer vision to embedded systems. And with just Python and few lines of code, you can build projects that would take far more complex setups. Thanks for watching and learning along. And I hope this series gave you the confidence to build your own computer vision projects with OpenMV.